Okay, we're continuing to explore families of transcendental functions. Let's focus now on the trig ratios. Their general form, and this may seem familiar, looks like amplitude times the trig function tan of the angular velocity times time minus the phase shift, and similarly for cotangent. And really we just need the first one because the second one can be attained using a trig identity. And yes, this is a note here that I'm going to put for everyone. You need to have your trig identities handy, and in fact maybe even memorize them. But let's see some graphs of the parent functions, which are, remember that the parent functions themselves are f of x equals tangent of x and g of x equals cotangent of x. So here goes the graph of tangent. And it's important to note that since tangent is essentially a ratio of sine and cosine, tangent is not defined for anywhere that cosine is equal to 0. And we said that the x-intercepts of cosine are specifically the half integer multiples of pi that are odd. So we can write that like this for all k integer. That means we're going to have vertical asymptotes there. And the quintessential graph that we'll draw for tangent is looking at the segment of tangent that's bounded between pi over 2 and negative pi over 2. So this is the essential segment that we'll be looking at when we graph tangent. But just be aware that tangent also is a periodic function. So it does repeat every pi. That means it makes it pi periodic. And you'll notice then from the shape of this graph that it passes through some essential points like 0, 0. It will pass through pi over 4, 1. As well as negative pi over 4, negative 1, which suggests that this is an odd function, and in fact it is. Let's graph now cotangent. So, similarly to tangent, we also have to be careful about vertical asymptotes. But this time, since sine is in the denominator, we're looking for the x-intercepts of sine, which are all the integer multiples of pi. So that means we're going to have a vertical asymptote right on the y-axis, as well as at pi and at negative pi. And this graph looks like tangent, but flipped across a vertical axis. So instead of increasing, it's decreasing. And in this case, it passes through pi over 2, 0. And it has these lines as vertical asymptotes. Again, it's periodic, so it repeats every pi. You have the same essential shape in between those two boundaries. So properties. Let's talk about what distinguishes these functions from others. For instance, we know that they're pi periodic. We also know that both are odd. And if you don't want to take my word for it, I can prove it to you. I'll just prove the case for tangent. So, in order to show that tangent is odd, we want to show that for all x in the domain of tangent, tan of negative x is equal to negative tan of x. Now, remember that tan of negative x is sine of negative x over cosine of negative x, where we know two things. First, sine is odd. So sine of negative x is equal to negative sine of x. Also, cosine is even, right? We established that earlier. So cosine of negative x is just cosine of x. It absorbs the negative sign. So, finally, tan of negative x is equal to negative sine of x all over cosine of x, which is the same as negative sine of x over cosine of x. And that recovers our original tangent of x. And we're done. Since this is the first proof that I've done in these videos, I want to just briefly go over the essential pieces of this proof. And this is common for any mathematical proof. You can think of a proof really as justification. We're showing why something has to be true. And depending on how complicated the task is, it can either be a short proof or a very long one. And in this course, we'll usually only look at very short ones. The essential pieces of this proof are what we want to be true. So what we're originally going to show, our claim, namely that tangent is odd. And I'll write that here. And then we have the actual justification steps, which is the meat of the proof. So we take some logical steps, such as manipulating equations, taking prior knowledge, premises that we know are true, and then lastly, we put it all together and we show that what we set out to show is actually true. And you end it with this, which is sometimes called a QED symbol. It means you're done with your proof. You can pick any symbol you want. Right, so both are odd. We have vertical asymptotes at the places that we specified, right? So for tangent, that's the half integer multiples of pi, and then for cotangent, we're looking at the integer multiples of pi, all right? And a few more things. For instance, we have unrestricted range for both. So both of them, you can attain any y value you want. And while tangent is increasing on every segment, on every interval, cotangent, on the other hand, is decreasing. They're monotonic over an entire interval. Okay, let's talk about the reciprocals. Trig reciprocals, remember that those are, our parent functions are f of x equals secant of x, and g of x equals cosecant of x. And the way we define them, they're graphs. I'll start with secant. And that secant is the reciprocal of cosine. So what we actually are going to do, my apologies, is we're going to fill in a graph of cosine first as a dotted line. And every time it crosses the x-axis, we're going to have a vertical asymptote. It should be reminiscent of what our discussion with the trig ratios, since we're dividing by some trig function, that it ends up being the case here. And so if we draw in our cosine curve, it should look something like this. And of course, we can match that on the other side as well. Which of course means that you have vertical asymptotes on the left side of the y-axis as well. And then our actual function graph will be bounded between the vertical asymptotes and just barely touching the cosine curve at its peak and at its lowest point. So here we have pi negative 1 as a point on the curve. We have 1, 1. Oops, 1, 1. No, 0, 1, sorry. We have 2 pi, 1, and a coterie of other points on that curve that are obtained just by taking the reciprocal of the cosine values. And you may guess, yes, this is also 2 pi periodic. So this fundamental pattern repeats. Now that we have that, we can talk about the graph of, so this is secant. And now we can talk about the graph of cosecant, which behaves in much the same way. Namely, we first fill in a graph of sine, and wherever it crosses the x-axis, is where we'll define our vertical asymptotes. And so here's the graph of cosecant. And yes, it does repeat every 2 pi, just like its counterpart, secant. Okay. So again, some important points are points like pi over 2, 1, and 3 pi over 2, negative 1. And some essential properties include things like both being 2 pi periodic, secant is even, cosecant is odd. And we've already discussed the vertical asymptotes for both. And importantly, the range will be from negative infinity to negative 1, including negative 1, union 1 to infinity. All right, so those are the trig functions. Now these are the parents. We'll discuss later other things that have to do with the trig functions. But lastly, just a note that we're going to discuss this later. So in section 1.4, we discuss exponential functions, which are also transcendental, and in 1.5, we discuss the logarithmic functions. And as we've discussed much later on in section 3 point something, I think it's 11, but I forgot at the moment, we discuss the hyperbolic functions, which are interesting in their own right for a number of reasons.